From the car you drive every day to the incredible spacecraft exploring our solar system, the technology we rely on is just unbelievably complex. So how in the world do engineers make sure it's all safe and reliable? Well, we're about to dive into a really powerful method designed to do exactly that.
I mean, that's the million-dollar question for any engineer, isn't it? When you're building something with literally thousands of interconnected parts, you can't just cross your fingers and wait for something to break. You have to get ahead of it, anticipate what could go wrong, and design those failures right out of the system from the get-go. But how?
And let's be real, the stakes for getting this right are just enormous. With today's complex systems, one tiny little failure can cascade into something catastrophic. This is exactly why having a systematic approach isn't just a nice-to-have, it's absolutely critical. So the answer to that huge question is a process called failure mode and effects analysis, or FMEA for short. The key thing to understand here is that it's not about finding problems after they happen. It's a proactive, structured way to brainstorm, identify, and prioritize potential issues so that, hopefully, they never even see the light of day. Now, you might be thinking this is some new corporate buzzword, but nope, not at all. FMEA is a truly battle-tested methodology that was forged in some of the most high-stakes environments you can possibly imagine.
Its story actually starts way back in 1949 with the US military. They needed to make sure their equipment wouldn't fail in the middle of a mission. Then, probably most famously, NASA adopted it in the 60s for the Apollo program. I mean, when you're sending people to the moon, failure is not an option. By the late 70s, the auto industry caught on and realized this was the key to making our cars much, much safer.
Okay, so how does this whole thing actually work in practice? Let's get into the nuts and bolts of the FMEA method. It's actually a very logical, step-by-step approach. At its heart, it all boils down to three big phases. First, you have to really, truly understand the system you're looking at, every single piece and what it does. Then comes the creative part. You imagine all the different ways it could possibly fail. And finally, you analyze all those potential failures to figure out which ones pose the biggest risks that you need to tackle first.
So that first step is called a structural analysis. The team literally creates something like a family tree for the product. They map it out from the main system, down to its subsystems, and all the way down to the tiny individual components. This gives everybody a super clear picture of how everything is connected and how it all works together.
Now, here's where it gets really fun. For every single item on that map, the team asks, okay, how could this thing break? How could it go wrong? What they're building is called a failure net. It's this amazing web that shows how one little cause of failure in one tiny part could cascade and create a big system-wide effect.
Okay, so you can imagine, after all that brainstorming, you've got this gigantic list of potential failures. You could get totally overwhelmed, right? So how do engineers figure out what to fix first? Well, this is where the process shifts from creative brainstorming to using some hard numbers.
They do this with a really clever tool called the Risk Priority Number, or RPN. Think of the RPN as the magic ingredient that turns a long list of what-ifs into a clear, prioritized action plan, and it's calculated using three really important factors.
First up is severity. This basically answers a very simple question. If this failure actually happens, how bad is it? Is it a minor annoyance for the customer, or is it a catastrophic safety issue? That gets a score.
The second factor is occurrence. This one's all about probability. Based on experience, data, and the design itself, how likely is this particular cause of failure to actually happen out there in the real world? That gets a score too.
And finally, we have detection. This score asks, with the tests and quality checks we have in place right now, what are the odds we'd actually catch this problem before the product ever leaves the factory? A low score here is good. It means we'll probably find it. A high score, not so good.
And the math to put it all together couldn't be simpler. You just take the score for severity, multiply it by the score for occurrence, and multiply that by the score for detection. And voila, that gives you the risk priority number. This calculation instantly creates a ranked to-do list of risks. A failure mode with a really high RPN, like that software glitch you see on the chart, immediately jumps to the top of the list. It tells the team, hey, pay attention to me. This is exactly how they focus their time and money to make the biggest dent in improving safety. But look, this process isn't just a numbers game. It's not just about formulas and spreadsheets. The real secret sauce, what makes FMEA truly effective, is the human element. A successful FMEA is always a team sport. You have to bring in experts from design, manufacturing, quality control, maybe even the sales team. This diversity is so crucial. because a manufacturing expert might spot a potential problem that a design engineer would never even think of, and vice versa. It creates a much richer, more complete picture of the risks.
And this is a really important point. An FMEA is not something you do once, put in a binder, and let it collect dust on a shelf. It's a living document. If a new law gets passed, or if customer needs change, or especially if you learn something new from products out in the field, you go back and update the FMEA. Safety is a continuous job.
So when you boil it all down, FMEA is really about a fundamental shift in mindset. The goal isn't just to get better at catching mistakes at the end of the assembly line. The goal is to build a process so strong that you prevent those failures from ever even happening in the first place.
It's a pretty powerful idea when you think about it. Just consider all the complex technology in your life, your car, your phone, even medical equipment. The reason so much of it works so flawlessly is because of this invisible, tireless engineering happening in the background, constantly asking, what could go wrong, so that for you, everything goes right.